this presentation to address those things. Guys, hold on. Are you getting a static? Are you getting an echo? I'm getting some echo. Prim's algorithm, Kruskal's algorithm, and so on, right? And one of the important concepts that we learned, even for when we talked about Dijkstra's open shortest path algorithm, all of those things rely on graphs, right? And then we said they rely on graphs, and then we said we introduced the notion of spanning trees, correct? That's what we did. And then we continued from there. But I never really got into any deep discussion on the theoretical concepts behind them, right, about graphs. So this one is like a brief glimpse into the theoretical concepts related to that. Nothing fancy, again, because this is not a math class, okay? If it was a math class, I would spend one semester on giving you theoretical concepts on graphs. And at one time, I used to be an expert in graphs. Long time ago at UT Austin, I actually took a graph theory class, which I aced it actually, and I took it from a professor who, at least at that time, was known as the top 3 professors in graph theory in the world. In the world, not just university, in the world. But this is not going to be at that level of detail, okay? Just some brief idea to say that, hey, how would it look like, right? So I will jump right into it. If you have any questions, you can always put them in the chat, and then if it gets too theoretical, too much discussion type, then I will reserve the right to cut short the conversation and say I'll post it in the community, okay? So if you recall, we talked about a spanning tree, right? So spanning tree is what? A connected, undirected graph with no cycles, okay? So, and it will contain, a spanning tree will contain what? All the vertices, right? Right? It should include every vertex of G, okay? And then every edge of the tree belongs to the graph. That is what we said a spanning tree is. It should not have cycles, okay? That is the main thing, okay? And it should have all the vertices of the graph. Okay. Now, and it's a subgraph of G. It's a subgraph because every edge of the tree belongs to G. We are not creating any new edges in the spanning tree, okay? What is the minimum spanning tree? It's a tree with the smallest total weight. If the edges have weights, whatever the weights may be, it could be distances, it could be anything else, communication, delays, whatever, depending on the problem context, a weight could be anything. A minimum spanning tree is nothing but spanning tree with the smallest weight. And as you know that both Kruskal and Prim, especially Prim, right? They use these concepts, right? So keep that in mind. So minimum spanning tree is the least cost subset of the edges of a graph that connects all the nodes. Okay. So here you have a graph, right? So what do we typically do? A generic algorithm, we start by, to come up with a minimum spanning tree, we start by picking any node, okay? There are many nodes here. You can call them A, B, C, D, E, F, A, B, C, D, E, F, yeah, whatever, A, B, C, D, E, F, yeah, 5 nodes, right? And adding it to a tree, okay? So when you're doing that, then what you do is repeatedly pick any least cost edge from a node in the tree to a node not in the tree, okay? And add that edge and a new node to the tree. So by doing these things repeatedly, you will come up with a minimum spanning tree. That is the algorithm. And then you stop when all the nodes have been added to the tree. Okay. So that is the concept, how you do that. Okay. So, and we did a lot of exercises on coming up with minimum spanning trees, right? If you recall, we did a lot of in-class exercises. Okay. So what are we doing here? Some animation is there. I didn't know that there's animation. Let's look at that. So we took 1 as the edge or the node, right? Start by picking any node. We picked 1. Then pick the least cost edge from the node in the tree to a node not in the tree. Okay. So from 1 we took the least cost. Least cost is 1 to 2. Other nodes are 4 and 4, right? And there are multiple trees from 1. You picked one of them. Okay. Then again you repeatedly do that. Okay. So by doing that repeatedly, you can see the illustration there, how we are building the minimum cost tree. One more node should come. There it is. That becomes your minimum spanning tree. Okay. So 3 plus 3 plus 2, 2, 2, 12. That is the least cost spanning tree by applying that algorithm. Okay. Now what happens if you think some other edge should be in the spanning tree? Okay. You can try to add the edge. Okay. If you try to add another edge, if it forms a cycle, then you cannot have. Remember, one of the conditions is you cannot have a cycle. Okay. So what is a cycle? Then that goes back to the definition of a cycle. Cycle is going from one node. I'm giving you informally, okay? Don't kill me for giving an informal definition. Let's say you start at 1. You can go from 1 to 2, 2 to 4, 4 to 5, 5 to 1. Okay, 1, 2, 4, 5, 1. That forms a cycle. The starting point and ending point are the same. And then you are not repeating the paths. The edges are unique. Okay. And you are visiting the vertices exactly once other than the starting and the ending node. Because starting and ending node are the same. That's the only node which you visit twice. That's a cycle. So you want to make sure there is no cycle in a tree. Tree does not have a cycle, right? So to break the cycle, what do? You must remove the edge with the greatest cost. Because by removing the edge with the greatest cost, you are ensuring that whatever you come up with is a minimum spanning tree. Right? The whole idea of minimum spanning tree is the total weight should be the lowest. Okay. Now we also said that there could be many minimum spanning trees. Okay. Not just one. Unless if all of them have the same weights. If all edges have the same weights. Same weights or, no, sorry, I think I said it wrong. Unless if all edges have unique weights. Okay. Meaning there are no weights which are repeated. Okay. Okay. So you can see to break the cycle, you must remove the edge with the greatest cost, and that will typically happen to the edge you just added. Okay. How is this MST problem stated formally? Okay. Some mathematical notation, right? So the input is G equal to VE, where G is the weighted graph, V is the set of vertices, and D is the set of edges. Okay. Now, the weights, of course, are going from edge to the real number. R is for real numbers, right? And then we are assuming that all weights are non-negative. Okay? So the goal is to find a spanning tree of G. Okay? A tree T, so I remember one of the faculty members said when you do the spanning tree, you will get n minus 1 edges Obviously, right? Because it should always be, there's some trivial proof for that. I think we covered it, or I don't remember. Because the moment it's always one less edge than the number of vertices. The moment you have same number of edges, then you will see a cycle. Okay. And then we want to get the minimum total weight of all the edges UV belonging to T, right? T is the tree. The weight of UV, meaning the sum of the weights of all the edges, is the minimum. So when you're trying to do that, basically you're transforming the problem into an optimization problem, because we're trying to come up with the shortest or the lowest weighted tree. Very interesting set of slides have come here. You will get some practice too, don't worry. Okay. So you have A belonging to A is part of the set of edges, denote the set of edges, right? So we say A is safe, keyword safe, right? If you have a minimum spanning tree of G, G is the total graph, right? So that A is a subset of T. Okay. So that whatever edge is there, we are always adding that only if it is the lowest weight, right? So by default, whatever minimum spanning tree you get, then A should become a subset of that tree, T. Okay. So what do we do? Step number one, initially it's a null set. Okay. So while A is less than n minus 1. Why? Because we always want to keep the set of edges in A as one less than the total number of the edges. Okay. So you find the UV, meaning UV is an edge. Okay. Where do you find that edge? You find that in E minus A. E is the total set of edges, right? And A is you are adding. So whatever you added, you subtract from E. So that way, when you do the A union, that new UV, it will still remain safe. Okay. So we gave the definition of safe up in the first line. Okay. So if it is safe, there exists a minimum spanning tree of G such that A is a subset of T. So the edge has to be a subset, and then you're always taking the lowest cost. Okay. So you go through that recursively. Okay. And at the end of the process, till you reach n minus 1 edges, you do that, you will have the set of edges which would result in the minimum spanning tree. Okay. Now, the question then is, right, how do you find the UV efficiently? Yes, somebody unmuted. Can you mute yourself, please? You're all getting big static. Okay, I can mute you again. Hold on, stop sharing. Find that UV is the crux of the problem. Okay. Now, in order to understand some of those concepts, because that is what Prim uses, right? Really, Prim or even Kruskal, when you're looking at the edges, you're looking at like, for example, I think was it Kruskal where we put them in the descending order of the edge weights. Descending, yeah. Actually, not descending, ascending, right? Lowest cost, and then the next lowest cost, and so on. Okay. So you need to understand a couple of theoretical concepts that go like, what do you call it, under the hood, right? Behind all these algorithms. So one is called the cut theorem. Okay. Let me ask you a question here. Are the students familiar with graph theory at all in any other classes? Did they do graph theory in intermediate, or did they do graph theory in engineering? First year? Can faculty members put some comments in the chat? cut theorem tell you? Again, theory, but I'll give you a nice example, okay, in just a minute. So basically, cut theorem tells you how to find that UV. What is the edge that you need to add? Okay. CISKKD saying my voice is not clear. If anyone else. Okay, so DMS said that they learn about graph theory in advanced data structures. When I say advanced data structures, you mean this class, or do you have another class called advanced data structures? You can put that in the chat while I continue, okay? So we need to know what cut theorem is, right? And I have good examples here, trust me. Even if you're lost now, hang in there for a few more slides, you'll understand what this is, okay? So how do we define this one? So what is a cut, okay? Second year, second semester, okay. So you learned graph theory in second year, second semester, okay? Good. So then you should tell me what a cut is, right? But I'll say it anyway, right? So when you talk about a cut, right? So you have this formal notation S, V minus S. So S consists of the set of edges or vertices in theory, which has those things which would cut the graph into two disjointed sets, two or more, okay? So it is a partition of the vertices where S denotes a non-empty subset of V, okay? And then we say that an edge UV belongs to E crosses this if one of its endpoints is in R and the other is in V minus R, okay? So, and then the next statement, we'll come back to the next statement shortly, okay? Because the next statement talks about the minimum weight. If the weight is the minimum among all the edges that cross, then it's called a light edge, okay? Let me jump to an example so that way it will become clear, right? So what is a cut actually? A cut is a partition. That means you're cutting the graph, okay? So a cut is a partition of the vertices. That's number one, okay? Number two, it is basically cutting the graph into two disjoint subsets, vertices. Ultimately, graph has all the vertices, right? So any cut determines a cut set, the set of edges that have one endpoint in each subset of the partition. So if you look at the red lines here, right? What are they doing, the two red lines? It is cutting, if by removing those things, you're cutting the graph into two disjoint subsets. And if you look at the edges there, one endpoint is in one subset, the other endpoint is the other subset. That is what a cut is, for a graph, okay? So a set means a set of edges, a cut set. That's a very common term, right? So I don't know if your internal exam, they ask you a cut set and so on. But nothing but a set of edges that have one endpoint in each subset of the partition, okay? And these edges are set to cross the cut. Okay, that's what a cut set is. Other important concept to understand prim, basically prim and Kruskal rely on these things, right? Is the notion of a connected graph. Okay, I defined some of these things even at the beginning, right? Remember, I think posted a small tutorial on graphs in our community, if I'm not mistaken. It's connected if there's a path between every pair of vertex. So here is an example of a connected graph where you can see that there's a path between every pair of vertex, meaning from every vertex, I should be able to go to any other vertex. Okay. Path doesn't have to be unique. It can be any path, okay? Another important concept related to graphs is the concept of a cycle. Because when you are doing the prim or Kruskal, I forget, when I come to that we'll see, every step of the way, I think crucial. Every step of the way, as we are adding edges to the set which belongs to the minimum spanning tree, we have to make sure that there is no cycle. Okay. So what is a cycle? Okay, a cycle is a circuit in which no vertex except the first appears more than once. Okay. I gave you an example of cycle in the graph earlier. Here is another example, right? So you can see a couple of distinct concepts coming here. Okay. In this graph on the left, you see the green one. That is a path, HAB. What is a path? Path is going, like I say that there's a path that exists between H and B because I can reach B via another node. Okay, that is a path. Okay. You have a closed path or walk with a repeated vertex. So if you see the things in blue, that's called a closed path, meaning like D, E, F, D, C, B. Starting with B, you're making a complete loop and coming back to B. Okay. However, if you notice, some of the edges are traversed or vertices are traversed more than once in that closed path, right? If you look at D, the vertex D, you're going through D 2 times. Okay. But that is still a walk. In graph theory terminology, we can call it a walk or a closed path. The distinguishing characteristic of cycle is there is no repeated edge or vertex. So if you look at the HDGH, there is no repeated edge or vertex. That is what distinguishes a cycle from a path. Anyone has questions on the difference between a cycle and a path? Closed path, or even a path. Okay, so far so good. So going back, I'm again tying all this back to the cut theorem eventually. So when you talk about a cut, right, you have, we looked at the cut set, which is a set of edges which would cut the graph into multiple subgraphs, right? You can have, like, you have a cut edge, you can also have a cut vertex. Okay. So what it means is if you delete the vertex, the graph would be disjointed. That is what a cut vertex means. If you remove that vertex, okay, it means see that if G minus V, delete V from G, results in a disconnected graph. Once you know the definition, it's very easy, right? So by removing a cut vertex from a graph, you're basically breaking the graph into 2 or more graphs. So I gave you an example here in this slide, which shows in the graph on the left, A, B, C, D, E, F, G, H. Okay. By removing either the vertex E or the vertex C, you're basically coming up with okay. Why somebody is not able to hear me? CIS. So if you remove that vertex, the graph is going to get disjointed. Okay. So C and D. In this case, what did I? If you do that one, you can see how the. 1 second. Why is my? Okay. So if you see that by removing either C or E, in this case I removed E, the vertex E. When you remove the vertex C, right, all the edges incident on E would go away because that vertex does not exist. That's the reason why you see the edge CE is gone, the edge EF is gone, and the edge EH is gone. Okay? Another key concept. Now here is the cut edge. The graph becomes disjointed. Okay? So in this case, if you remove the edge CE, then you will be left with 2 disjointed graphs. Okay? So you have cut vertex, you have cut edge. Everyone understands those 2 concepts? Excellent. Now we are going back to the cut set. Okay. So a cut set, when we talk about a cut set of a graph G with vertices and edges V and E, okay, of a connected graph, we have a subset E of E prime, right? We call it E prime, right? That apostrophe there of E is called a cut set of G if deletion of all the edges of E prime from G makes G disconnect. Okay. So if you were to put it in other words, if you're deleting a certain number of edges from a graph, makes it disconnected, then those deleted edges are called the cut set of the graph. Okay. I think I have some example here. What is the cut set here? As you can see here from this graph, I have, if you remove edges E1, E3, E5, and E8, E1, E3, where is E3? E3, E5, and E8. Okay, you're going to get two disjointed graphs. I'm pausing so that way you can visualize that. Okay. I was actually I was thinking I'll make it as a group exercise, but I did not. Okay. Now, one more concept here. These are all concepts tied when people came up with prim algorithm and Kruskal algorithm, and they started proving stuff as to why they result in minimum spanning trees. See, what happens is, right, when you're a researcher, when you're giving a solution like a prim or Kruskal, right, you have to prove the correctness of the algorithm, which we no longer do now, right? In the real world, we don't prove I have a deadline to meet, I have a project to do, and then I have to earn money. When I write an algorithm and I write the code, as long as it works that day, not even like forever, that day, then I'm done. I'm not sitting there proving all this stuff, but as a researcher, when you're writing papers, you do have to prove. That's why you need all these concepts. So what is edge connectivity? Okay. If you have a graph, okay, and the minimum number of edges whose removal makes G disconnected is called edge connectivity. Okay. How many edges you can remove to make the graph disconnected? That is the edge connectivity. Okay. So the number of edges in the smallest cut set of G is called the edge connectivity or G. Okay. Interesting, right? You don't have enough knowledge and skills yet to extrapolate this thing to real world. How do we apply this to real world? I'll give you an example. Because I'm a security researcher, I consult, I publish papers. Okay, this is called the vulnerability analysis. Actually, even in your electrical engineering courses, you would learn some of these things, right? If there's only one path to go through, if you cut off that path, then you cannot reach the destination, right? You are only as strong as the weakest link, as they say. Okay. Let's say if there's only one bridge to go to a town, okay, and then you cut off that bridge, you bomb it, then the town is isolated. Okay. So there are some very practical applications of these things. So when we are analyzing problems, right, we actually do graph modeling, right? So doing that, we look at edge connectivity. If I see an edge connectivity of 1, that immediately tells me there's a vulnerability. Okay. If you notice here, I thought somebody would bring that out here. In this graph, really by removing the edge E9, am I already creating disjointed graphs? So the minimum cut set here really is 1, right? E9. If I remove that edge E9, I don't have to do the cut set E1, E3, E5, and E8 to get disjointed graph. I could have just removed E9 and then I would have gotten a minimum cut set. Okay. I'll have some fun soon. Okay. So I have some example here. I don't know if I have an answer or I just put it there. What is the edge connectivity for this graph? Can somebody take a minute? So edge connectivity is how many edges you have to remove to make a graph disjointed. 2. Okay, tell me what the 2 edges are. Is that the only solution? To destination and so on. Okay. Great. Let me go to the next slide. Okay. Now we have vertex connectivity, similar to edge connectivity. The minimum number of vertices is removal makes G either disconnected or reduces G to a trivial graph. It's called a vertex connectivity. Okay. The notation used is KG. So here is an example. So what could be the answer for this vertex connectivity example? Which vertices you have to remove to make this graph disconnected? I suddenly had a question myself, okay? I was looking at your answer there. Yeah, if you remove A, yeah, A is out of the loop, but the rest of the graph is still connected, right? Is it still called connected? I have to verify that. See, what happens here is, right, if you look at the edge connectivity, by removing the edge, the graph is definitely disconnected. Because you can see like E9, when I remove the edge, the vertices, there's no way to cover all the vertices. So here, what are you saying? Okay. So C and E. So by removing C and E, okay, what would be the graph C? All the, okay. So you get ABD. I can still go to ABD. From A, I can still go to I, J, G, F, H. So I'm still able to traverse rest of the graph, right? So is that, does it mean that is it still connected or not? I have to check some concept. If somebody wants to CJ, there you go. Okay. So C and J, there you go. Correct. So if you remove C and if you remove J, then the graph is right. So if I remove C, I can do ABD, I can go to I, and J is no longer there. That means I cannot go to the right side. And then E is E and I. So E and I also, same thing. If you remove E and I, it becomes disjointed. You got it. Okay, those are the right answers. Okay, you are thinking better than I am today. And I did not even get drunk yesterday. New Year's Eve celebration. Okay, thank you. Sri Prakash, I think you gave the good answers there, both DMS and Sri Prakash. Okay. Now, what is the degree of a graph? Okay, this is another concept related to some of the things that we are learning, right? So you have a graph and V is a vertex of G. So for each vertex, there is a degree. The degree of V is the number of edges that are incident with V or incident on V, as we say, right? The only exception is if you have a self loop that is counted twice, okay? And then you are given the total degree of G, which is nothing but the sum of the degrees of all the vertices of G. So I have a graph here, disjointed graph, okay? So what is the degree of this particular graph? If I ask you that question, what is the degree? When I say what is the degree, then how would you put the answer here? So degree is 3 is what? You could be wrong. That is the total degree of G. Is that the total 3? I get 3, 4, 5 different answers. Okay, I got 3, 4, 5. A lot of people said 4. Don't put privately, put it for everyone. We are just having fun here, okay, as a group exercise. Sri Prakash said yes. Yes for what? You gave an answer up. Let me check what answer you gave. Sri Prakash said 3. 3 is the total degree of the graph. Is that what you're saying, Sri Prakash? Okay, let's check. Did anyone give total 6? See, they answered there, right? So degree of V1 is 1 incident. Degree of V2 is 4. Why is this 4? Because it has a self loop also, remember? That counts as 2, and then you have E3 edge and E1 edge, that's 4. Degree of V3 is 1, degree of V4 is 0, and then the total degrees, you sum up all of them. That is the definition of degree of a graph. The answer is 6. Actually, by the way, I should tell you, even I forgot what the degree of a graph is. I suddenly blanked out when I was preparing for the lecture. I blanked out. I had to go and then go back and review my notes and then figure out what the degree of a graph is. But this also proves my point, right? So who will remember all of these things, right? And all of you gave so many different answers. I myself admitted that, hey, I blanked out on what the degree of a graph is. I had to go look up the definition and then do it, right? That is the point of all of this mathematical analysis, right? It reminds me of my favorite scientist, Einstein. How many of you know that Einstein was very poor in math? I mean, he's still a genius, okay? But he hated math. All the mathematical proofs that Einstein had in his E equal to mc squared paper and all of that stuff, general theory of relativity, special theory of relativity, he had to rely on his friends who are mathematicians to prove those things. Okay, just to give you an idea about proving and formalism, correctness, safety, and all that. So I have become, as a practitioner, I take all of these things with a grain of salt. I say, hey, whenever I need to look up, I can go look up. Right? Otherwise, I forget them. Okay, so where does all of these things lead to? So there's a big equation that comes to, that brings all of them together. For any connected graph G, Kg, that is the vertex connectivity, is less than or equal to the edge connectivity of whatever that symbol. I don't know what that symbol is called, by the way. Okay. I hope you are not asked questions related to this in your internal exam. If they do, then good luck to you. Okay. Now, where does all of those things lead to? Okay. It leads to our favorite Prim's algorithm and then Kruskal's algorithm. Okay. So just as a refresher for you, what does the Prim's algorithm do? It starts with any root node, and then it keeps adding edges with the smallest weight. That is the main small delta. Thank you. Yeah. It comes from small delta. Okay. Let me go back to that. Let me, yeah, small delta. Okay. Thank you for clarifying that. I forgot all those notations now. Okay. So Prim, starting with any root node, add the frontier edge with the smallest weight. So far, so good. Okay. And then, so it starts with a node and then goes with the edges, right? Prim. Whereas Kruskal, it actually puts all the edges in increasing weight, right? So it starts with an edge. Then every vertex, it's like we call it a forest, right? So then you have the forest, whereas in the case of Prim, there's only one tree. Okay, you're building the tree. Whereas in the case of Kruskal, you're starting with a forest, meaning every node or every vertex is a tree by itself. Forest has multiple trees. Then you start adding edges. Okay, that's the difference between Prim and Kruskal, right? Okay, see how all this theory is coming into play. Okay, I don't know if this is what PVP Siddhartha wanted. Past class, this is the kind of stuff. This is all in your honor. Okay. So you should be a happy camper today. Whoever the faculty member is there. Okay, he must be smiling, or she. Prim's algorithm. So you're starting with any root node and you're adding the edge with the smallest weight. And then the theorem says Prim's algorithm produces minimum spanning tree. We all said that, right? That's the algorithm, but how? But they have to prove it, right? That it is producing a minimum spanning tree. Only then the community will accept that, yeah, it is an algorithm which is right for producing a minimum spanning tree. Okay, so this is, if you see that the set of nodes already in the tree, remember what is the thing that they are doing? You're adding the nodes, you're adding the edges, right? That's what Prim's algorithm is. Start with a root node and add an edge with the smallest weight. You see the dotted edge that you see there, EUV. Okay, so when you're adding that edge, okay, then you have to make sure that there is no cycle that is forming. Remember, when you're adding the edge, you have to ensure that there is no cycle. That is the essence of it, right? And we define what a cycle is. Okay. Now, how do you do that? They make use of what is known as cycle property. Okay. So what is the cycle property? Prim makes use of this particular property to ensure that, to prove that their algorithm works. Okay. So how does this look like? I do not know if they ask you what a cycle property is in your internal exam, but here is it. Okay. I may or may not understand the full essence of it, but I'll try to give it my best shot. Okay. So let's assume that there is a cycle in G. Okay. Okay, that ABC. If I draw a triangle, the smallest cycle is ABC. Okay. And then one of the edges, let E is the edge, right? UV be the edge with maximum weight on C. Okay. So if that is a maximum weight, then what we are saying is that edge is not in any MST of G. Okay, because the whole idea is it has to be minimum weight, right? Whereas you're adding the maximum weight on that particular cycle, then it cannot be, that edge cannot be part of the minimum spanning tree. That's what he's trying to prove. Okay, how is he proving it? There are different types of proofs, right? Proof by induction, and this is a proof by contradiction. right? That means we assume the theorem is false. Then we arrive at a contradiction. Once we arrive at a contradiction, we say then our assumption that the theorem is false would be incorrect. So the theorem is true. That is what proof by contradiction is. Okay. So we are assuming that the theorem is false. That means we are assuming that there is a minimum spanning tree that will contain an edge which has the maximum weight. Maximum weight, correct? So when you're deleting E from T, okay, when you're deleting that, what you're doing is you're using the Cutset property here, right? Or that's what it is. Deleting E from T partitions vertices into two sets. One is a set S that contains U, and then you have the V minus S that contains rest of the vertices. Okay. Then you are saying that the cycle must have some other edge F that goes from S and V minus S. Okay. Now when you have some other edge there, because it's a minimum spanning tree, right? So by replacing E and F produces a lower cost tree. All right. So one, you assume that E is a big high cost, but if there's another edge F that is going from one set to the other, by replacing it, you are getting a lower cost tree, and which contradicts that T is an MST. So simple proof like this. Okay. Now, how do you understand these theorems? I do not know how these things are taught in JNT or institutes there in India now. I can tell you my personal experience of understanding a theorem. When I have a theorem like this, I'm going to do a test. Because I'm a software engineer, I love to take test data, right? So go back, revisit some tree like that, a node like this, take a concrete example of a graph like this, and then do that. Okay. Hopefully you don't have to prove these things in the exam though. Or if you have to prove, maybe prove with an example, right? So he makes you a cycle property, and he gives you a visualization. What is the cycle property? What I just explained is what you are visualizing here. See this E here? You have the set S. This is the set of edges which are part of your spanning tree. Okay? That's what we are doing, right? We are adding edges, lowest cost edge. And V minus S is all the rest of the set which do not have these vertices. Remember, the minimum cost spanning tree the tree should still have all the vertices. So you have some vertices here, and then you do not minus of that, V minus of that is this one. And you're trying to add this UV. Okay. But by adding that, you're forming a cycle, whereas there's another edge here, F, which has a lower cost than UV. Okay. Then it violates the assumption that we made. That's how you prove it by contradiction. Okay. Now I'm 100% sure that I probably lost 80% of the class in these proofs, but it's okay. These proofs cannot be understood in class. You have to spend hours understanding them by working on examples, okay? I'm just laying the foundation here for you. So now you can go back and see the minimum set property summary. So use the cut property. The smallest edge crossing any cut must be in all minimum spanning trees. Okay, that is one property that you use. Remember, we talked about the cut. Okay, and then the cycle property, the largest edge on any cycle is never in any MST. Intuitively, it makes sense, right? So, because when you have the largest, there's the largest weight, right? So how can it be part of a minimum spanning tree when we are saying minimum spanning tree is if you sum total the edges weight, that should be the lowest cost, okay? Now, when it comes to Kruskal algorithm, similar thing. Here, what we are doing is instead of taking the root node and then adding edges, we start adding edges and increasing weight. Now, as you're adding edges, you have to go back to the cycle property and make sure there is no cycle. Okay. So I don't think I went deep into this one, but by as long as you are, what do I want to say here? Let me think. Yeah, I don't think I really want to say anything. I just put one slide here, and I think my impression was you should go look for the theorem and the details related to Pruskel's algorithm. But the picture is important here, right? When you are adding this edge, right, you have to make sure that there is no cycle. Because if U and V, if V is already here in this one, this set, if you're adding another edge UV, you can show that UV forms a cycle. And as long as you don't form a cycle, you can come up with the minimum spanning tree in Pruskel's algorithm. Okay, that is that. Again, I didn't go through the full details of Pruskel. I want you to do it more like a take home. Because I showed you Prim, similar concept for Pruskel. To satisfy the folks here who love theory, picked up some examples from some exercises that I came across. These are the type of exercises that are given when you're talking about graphs and all of these things, right? Let's take a look at one of them, right? What does it say? Let E be a minimum weight edge in a graph G. Okay? You have to prove these propositions. Then UV is contained in a minimum weight spanning tree of graph G. So how do you prove that? Okay. Similarly, BCD. Okay. If I go here, I show you, again, I'm not going to spend 45 minutes trying to discuss the proof here, but I'm giving you the answer also there. So that way you can see how how people come up with these proofs. So that is you can call it like lemma or a proposition, right? So you can see the answer there. He's saying, okay, so we are going to take a minimum weight spanning tree, okay? And then we prove by contradiction, right? Because all minimum weight edges should be in the minimum spanning tree. That's intuitively we know that, right? So we are saying that, hey, we are saying, okay, let's assume that it does not contain that edge to begin with. Then we add that edge to the spanning tree. Okay. Now, since by adding that, you're going to form a cycle because one of those vertices is already in the set. By adding that edge, you're forming a cycle. Okay. Now, that means you have to remove one of the edges, some edge E prime, which is not E, which belongs to the cycle. Now, once you remove that, you get a new spanning tree, T prime. Okay. Now, since we removed another thing which is not the lowest cost weight, right? Because you removed not E, but E prime. Okay. And E prime's weight is more than E, right? So the weight of spanning tree T prime is not more than the weight of spanning tree T, because the weight of E is not more than the weight of E prime. So again, using proof by contradiction, you are able to show that T prime is also a minimum weight spanning tree in graph G, and T prime contains E. So most often you use proof by contradiction or proof by induction to prove such theorems. Theorems or propositions, whatever you want to call them. I gave an answer to B also. Similar thing, let E be maximum weight edge. It's the opposite of that, right? So then we are saying that there exists a minimum weight spanning tree of graph, okay, with E, which is also minimum weight spanning tree of the graph G. Okay, some proof here. Again, convince yourself. Take a paper, pencil, put some graph with numbers and go through that, and you can convince yourself how to prove it. I think I have one more example, which I think I did that. Same thing for C. Okay. So that's where this stops, the theory part. When those algorithms were published, all these proofs were given actually as part of the papers too. Questions, comments? Okay. PVP Siddhartha, I think were you the one or C Prakash who said that something about theory on sites as I can see here, okay? The beginning, right? So this review will consist of the review of all the 3 chapters, so that way you are in good shape for the final exam, okay? I mean midterm or internal as they call it, right? And then we will continue that next class also, okay? So we started off, what did we say? We said this is a design and analysis class, and then the first and foremost thing that you need to know is complexity analysis. This class is about understanding complexity analysis of algorithms, right, which you design, okay? So we said that, if you recall, I gave you a small example here. I said, hey, count the number of instructions. Okay. Can you guys hear me? I'm just checking again just to make sure that can you hear me? Every now and then I check to make sure that you are able to. Perfect. Okay. So you know how to count the instructions, right? So again, when you count the instructions, different students might do it slightly differently if the problem statement does not give you clearly as to how to count the instructions. Okay. If you look at the var m equal to a0, that is 2 instructions. In some other languages, it could be considered as 1 instruction. In some other languages, it could be considered as 4 instructions. Who knows, right? But standard thing is lookup. Array lookup is 1 instruction. Assignment is another instruction. Okay. So if the problem does not give you the directions clearly, then you have to state your assumptions there in the internal exam, saying that, hey, I'm assuming that array lookup is 1 instruction and assignment is another instruction. Okay. So then you have the for loop. Okay. We have done the example there, how we come up with it. I equal to 0, I less than n, I plus plus, right? So you, at every stage, I gave you the number of instructions. Okay. Then we said the important takeaway for this one for you would be, okay, the Fn is going to be 2 plus 2 plus 2n plus 4n, which is equal to 4 plus 6n. And then we said since we do asymptotic analysis, what it means is, or asymptotic behavior, what it means is we drop all the factors and then we keep the largest growing term. That is the essence of asymptotic behavior. So by doing that, we are saying that this particular function is of the order of n. Because you drop 4 first, it's constant, and then you drop the factor 6 because as n grows larger, 6 is meaningless. So we say Fn equal to n. Okay. I can envision multiple questions which would make you do this in an internal exam. Okay. Because in one shot it will execute constant. Okay. Excluding recursion. Remember recursion, we talked about n factorial, remember? So you can see that how the recursion is it does not apply to recursion. Okay. And then any program with a single loop which goes from 1 to n will have function n equal to n. So if you look at the standard matrix multiplication, where you have nested for loops, right? For I equal to 1 to n, for j equal to 1 to k, and for something equal to something, like 3 for loops you get, right? For matrix multiplication. The moment you see nested for loops like that, it's order of n cube. So the easiest way, instead of counting literally each and every line of code, if you look at the for loops, that will give you most of the story, most of the time, especially in an exam. Okay. So I gave some code here, and turns out I also gave you the answer there. The reason why, what does this program do? It finds duplicates. I do not know if in your internal exam they'll ask you a question saying write a program to find duplicates. Because I don't design your questions, right? I'm here. But if they do, you can see there are two for loops there. Applying the rule of two for loops, so you can see my question to answer the function n equal to order of n squared. Make sense? Okay. So here is a question to ponder for you. Okay, integer I for I equal to 0, I less than n plus I. And then I'm calling function b. And function b has n instructions. Okay. So what is fn there? Think about it. If you know the answer, you can put it in the chat. Okay. These are simple things. That's a exam question right there for you. Notation. So JITS gave the answer as n plus 1. N plus 1 means it's n only, right? Remember, you drop all the lower order terms, right? Correct? So that means you're saying it's order of n. Does every college agree that it is fn equal to n? Equal to n squared. Let me make it easy for you. Plus 12 theta of 2n, right? And then this notation is what we call it as time complexity. And there are three notations that we use, right? Big O, big theta, and big omega. Okay, there are three complexity notations. Okay. So why do we use big O notation? Because it's very hard to find out the exact behavior. Okay, unless for trivial examples, it's extremely hard for complicated algorithms to come with exact theta. Okay. However, as you see in the second bullet, right, we can always come with the worst case, meaning, hey, we know what the upper bound is, meaning it can't be worse than that. Okay, so that upper bound that we talk about is the big O notation. So I gave you an example here. Right, and then I'm asking, these are the type of things that will be asked in your exam, by the way, right? So here's an example, some pseudo code. And then I'm asking what the complexity is, okay? One for the loop, n times, the second for loop, right? Another n times. Simplifying those two loops, we get O(n) squared. It also turns out it is theta n squared. It's a small piece of code. I was able to calculate the exact. When I say exact, remember, I'm still dropping the constants and lower order terms. Okay. We have shown examples where something order of n squared may not be theta n squared. Okay, not always. The equation may not hold true all the time. I think we did some examples. I don't know if I put them in the review here or not. Okay, and I think we did an example like this: true or false, right? Which of these things are true and which of these things are false? You may want to review your answers that you gave. I don't know if I captured the answers here, but if you go back to your slide deck, we have answered these questions. Okay. So O complexity gives you an upper bound for the actual complexity. Theta gives the actual complexity, okay, also known as the tight bound, okay. So if we do not have a complexity bound that is not tight, then in those cases we use the lowercase o to denote that, okay. Now most often we are lazy, okay. We just use big O. Even though sometimes it's not a tight bond, you're supposed to use small o, okay. We say in casual writing, we just write big O. We just call it big O. Now in a test though, when they ask you whether it's a big O or a small o, you have to be careful. Okay, if they say this is not tight bound, then that should trigger a thought in your mind, hey, there should be small o. Okay. Okay. If it is an order of theta n, then obviously tight complexity is n. Okay. Whatever algorithm is n, it can also be easily made to order of n squared also. Remember, you can make something worse. A good program worse, right? That's why anything which is order of n can also be made order of n squared. I can simply add another useless for loop and I can make it an order of n squared. Okay. If they both have the same bound, order of n and theta of n, then it's a tight one. Okay. When something is not tight, as it shows here, order of n squared bound is not tight, we can write that as the small o of n squared. Okay. So I gave an exercise in the class that we did. I copy pasted here, so that way you can review these things when you go to the test. Again, the solutions were given in our deck, so you should review these things and then answer them. Compare your notes again with what you have done in the class. Okay. But the important thing to know is the O complexity is much easier to find than theta complexity. Okay. Then we introduce the omega notation. Okay. So the omega notation basically is the other one, while big O talks about the upper bound, this talks about the lower bound, meaning it will never be slower than a specific bound, worst case analysis. As it says here, if we do the opposite and modify our program to make it better, right, we use the notation omega. Okay. So that means the complexity, we know it can't be better than that. That is the best that can be done. Okay. Big O says that is the worst that can happen. Omega says that is the best that can be done. Okay. So when you say omega of n cube, it means the algorithm isn't better than n cube, meaning you can't improve it further. Okay. So you have the upper bound, you have the lower bound, and you have the exact bound. Those are the three corresponding to the big O, theta, and omega. Okay. And then I gave the same exercise. We did these exercises. I repeated them here, so that way it's a reminder for you to go and revisit those things and then write down the answers. And the way I would recommend preparing for the internal exam is by doing it in groups of 2. Remember, I've always asked you to do it in groups of 2 or 3. Do it like a study group and then prepare and you will be just fine. Okay. So as I say, O is the most commonly used one. Okay. Okay. I will stop here for today and then see if you have any questions, comments. If not, we'll continue in